Okay, welcome everyone. This is a great occasion because I think it's the first time we've done a proper webinar seminar that goes, well, hopefully that doesn't go wrong. And it's good to welcome people from Cambridge and from the Rutherford Appleton Lab and a number of other places I can see. And some people from across the Manchester site who obviously can't walk here to this meeting. So welcome everybody. And it's also a really great pleasure to welcome Harry. For those of you who think that I am an enthusiastic lecturer, you have seen nothing yet, because Harry is one of the most enthusiastic and infectious enthusiasts I know. He is really Mr. Steels, and so when we were looking to put together our bid for the ICAM, we could think of no one else we could ask to get involved in alloy design than Harry, because he is really a world-renowned expert. Not only is he a professor in Cambridge, which is a full-time job in itself, he's also a half-time or a third time? Half-time. Third time. A third time a professor also in Korea. And so he has two big groups that he runs really efficiently. And anyone has ever, if anyone you have never been to his website, I think he gets probably more hits on his website than the Manchester Material Science Department and Cambridge Material Science Department put together. So again, if there's anything ever you need to know about metals, the first place, or I always look, is Harry's website. So again, I recommend his website, which is a really fantastic a source of knowledge. Anyway, enough of me. Harry, we're really pleased to have you here and to be our first ICAM webinar lecture. And over to you. Thank you very much.
Thank you very much, Phil. Now I hope that the lecture goes really well. Otherwise it will be a big letdown, I can tell you. So today I'm going to give this lecture for the first time. I haven't talked about this before, although we've been working on hydrogen in steels, the particular aspects that I'm going to talk about, for some time now. And I thought I would begin by summarizing units, because remember, we are working in an international environment, and often you see units of hydrogen in steel quoted as centimeters cubed per gram, or parts per million by weight, or parts per million of atoms in the whole assembly of atoms. And similarly, we often talk about PSI, pounds per square inch. So this is the conversion unit between pounds per square inch and megapascals. Now I'm going to begin. Hydrogen is a very, very confusing subject. Hydrogen in steels is a very confusing subject with vast numbers of publications. I'm going to begin by summarizing what we know, which is beyond doubt. Okay? So the first point that I'd like to make is the iron-hydrogen phase diagram. Basically, what you can see from here is that there is a significant solubility of hydrogen both in ferrite and in austenite. The solubility in austenite is much greater than in ferrite. Although, as you'll see later, the mobility of hydrogen atoms in austenite is orders of magnitude slower than in ferrite. So there's a slight contradiction that the solubility in austenite is much higher than in ferrite, but the mobility of hydrogen in austenite is much, much slower than in ferrite. The units here are atomic percent of hydrogen. So although this is actually a small concentration, like all interstitials, it has a very, very large effect on mechanical properties. And understanding why it has a very large effect is what this talk is about. And indeed, in controlling the behavior of hydrogen inside the steel, so that even if we don't know the mechanism, can we stop it from doing damage? Now, it's a mistake to think that hydrogen only influences polycrystalline materials. In other words, very often when you get fracture, you see intergranular fracture. This is an experiment done in 1926, and they grew large single crystals plus polycrystalline iron and observed dramatic effect on the embrittlement of iron by hydrogen. So the top tensile specimen is an uncharged specimen, no hydrogen introduced, and you see a remarkable change in the ductility when you charge it with hydrogen. Okay? So it's basically almost brittle failure with virtually no reduction of area in that specimen. So actually this isn't the earliest paper. Later on I'll show you one from 1875, because there's a process called pickling. Pickling is where you try to remove surface sponge from the steel, and of course you do that in acid, and therefore you introduce hydrogen into the material, and people spotted that when you pickle steel, the properties change dramatically. So there is absolutely no reason to do an experiment to show that hydrogen embrittles. Okay? Well established. The next thing is that the tendency to embrittle more or less correlates with the strength of the material. In other words, you get greater embrittlement as the strength of the material increases. Okay? Now, we are, of course, interested in designing stronger steels. So this problem becomes worse as you go towards strength levels in excess of, say, 500 megapascals, and that's quite a low strength. Yeah, we want to design, for example, pipe materials for BP where we will get strengths of the order of 1600 megapascals. That means that hydrogen becomes an enormous challenge. I mean, look at this. If we had 200 parts per million of hydrogen in that particular steel, then we would basically have zero ductility. Now, you could argue that is this really a correlation against strength? Or is it that when we make a high-strength steel, the starting ductility is low, and therefore when you introduce hydrogen, you get more or less no ductility? Well, again, this has been studied, and you can see that it isn't the case that the stronger steel starts off with lesser ductility. No significant difference in the ductility of the uncharged specimens, but you get a dramatic decrease in the ductility in the stronger steel than in the steels which are not as strong. So there is a clear correlation. Okay? Now you can think of many ideas, none of which seem to be proven of why this should happen, but the fact is that when you make a stronger steel, the problems with hydrogen become more severe. And it isn't to do with the fact that they may have a lower ductility. This is a summary of the diffusion coefficient of hydrogen in ferrite and in austenite. And that ferrite and that austenite is more or less defect-free. In other words, we're doing a perfect experiment to measure the diffusion coefficient in ferrite and a perfect experiment to measure the diffusion coefficient in austenite. And you can see orders of magnitude difference in the diffusion coefficient. So you might ask yourself the question, how can we hold hydrogen in a steel cylinder which is ferritic? I mean, you do it, right? Any ideas? How can you hold hydrogen in a steel cylinder? The diffusivity of hydrogen in ferrite is huge. Well, this is atomic hydrogen. Okay? Molecular hydrogen hardly enters the steel. So the cylinders contain molecular hydrogen, and similarly, if the hydrogen in the steel changes into a molecular form, for example, by entering a hole, that will not be able to escape out of the steel. Okay? Now, this shaded region on here shows the reality, because you are not really going to make steels which have no defects. You will have various kinds of defects. You'll have grain boundaries, you'll have inclusion, interfaces, you'll have dislocations, and so on. And like carbon, interstitials prefer to be in locations where there is a bit of space. Yes, the strain field due to interfaces or dislocations attract the hydrogen, and therefore, in order to move, they have to come out of that potential well, and therefore the actual diffusion coefficient in ferrite, it's been known since the days of Darkin, 1945, that the actual diffusion coefficient you measure will be far less than the diffusion coefficient in ferrite, pure ferrite. that isn't the case for austenite. You know, the activation energy for diffusion in austenite is so large that you can regard almost every lattice point as a trap. So I don't have a corresponding shaded region here for austenite because basically the diffusion activation energy is of the order of 55 kilojoules per mole, which is greater than many of the binding energies of hydrogen to defects. So this is well established stuff again, and you'll find hundreds and hundreds of papers on trapping. Now I'm going to sort of very briefly go through some of the proposed mechanisms for hydrogen embrittlement, and one of the classic one is that, you know, small concentrations of hydrogen, and we're talking about parts per million of hydrogen, influence the surface energy. Okay. So supposing that hydrogen makes it easier to cleave iron, then the embrittlement effect is very easy to explain. So we did some first principles calculations because it's very hard to prove whether hydrogen reduces the surface energy at a concentration of a few parts per million or not. Hydrogen in ferrite, unlike carbon, occupies tetrahedral interstices. It sits most comfortably in tetrahedral rather than octahedral interstices. This is tetrahedral, octahedral would be in the middle of that object. Whereas in austenite it sits preferentially in the octahedral interstices. So what you do is you take a number of atoms in your computer, you place a hydrogen atom inside that cluster, and then you have to cleave it. Now how do we cleave this? Well, the spacing between this layer and this layer is much larger than the spacing here, and you increase that vacuum space until it doesn't make much of a difference to the total energy of the system. That means you've created a cleavage of material, and then you work out whether hydrogen reduces the surface energy or not. And just to test whether things are in the right direction, we know for sure that the segregation of carbon to grain boundaries, for example, strengthens the boundaries rather than embrittles. And that means that we should actually get an increase in surface energy, because to create a surface is more difficult if you increase the surface energy. And the results indicate, yes, indeed, there is a reduction. This is for hydrogen and this is for carbon. There's a reduction in surface energy when you add hydrogen, and there is a slight increase when you add carbon. And the same for austenite. But you know, this is not something to write home about. It's a very small difference that you see. It can't really explain what we observe. And furthermore, in these first principles calculations, the concentration of hydrogen is much higher than in reality, because we are limited to, computing power limits you to cells which are not very, very large. So if you add one hydrogen atom, that's 1 in 100 perhaps, as opposed to 1 part per million where we have the effect. So it doesn't seem likely that the effect of hydrogen is to reduce the surface energy and therefore to make it easier to cleave iron. This is another classical mechanism where hydrogen migrates to points where there are stress concentrations, and there it might convert itself into hydrogen molecules, precipitate, and so forth. And when that void that you create, which is full of hydrogen, is small, then the pressure in there is enormous. Just like when you start to blow a balloon, it's very difficult at the beginning, but as the balloon becomes larger, it's easier and easier. And this isn't really how it happens, because here we are surrounded by solid steel. But just imagine the shell. If you work out the pressure that's trying to push the two halves of the sphere apart, then it's the force that is trying to push the two halves of the sphere apart, then it's the cross-sectional area times the pressure. And what's holding it together is the force in the shell, which is 2 pi r times the thickness times the surface energy, and therefore you will see that the pressure inside the bubble scales with 1 upon r. So when it's very, very small, the pressure will be very high, and you can imagine circumstances in which that will nucleate cracks. Okay. So that's one possibility. But for this, you need to form voids, and I'll come back to this later. So this goes back to 1941, and it's still a mechanism which is respected to some extent. Now, this is the 1875 paper on hydrogen embrittlement, where there were some remarkable changes produced in iron and steel by the action of hydrogen and acids. I have actually edited these lines to make them shorter. And it's caused by its temporary immersion in hydrochloric acid or sulfuric acid. There is an extraordinary decrease in toughness and breaking strain of the iron, but this change is only temporary. That means if I charge the material with hydrogen and then let the hydrogen escape from the steel, you recover the properties. So any mechanism that you propose should be consistent with the fact that you can recover the properties. And I'll show you another graph. This is the stress strain curve for a piece of iron without any hydrogen charging, the flat curve. Okay? And it's true stress versus true strain, but necking strain is somewhere here. If I allow the specimen to rest for 1 hour after charging with hydrogen, then I get to this strain. If I allow 21 days for it to rest after charging, then I almost fully recover the ductility. So any mechanism that you think about has to be reversible. One experiment which, as far as I know, hasn't been done is to see whether the effect is reversible if you put a notch in the sample. Because then, supposing you create voids in the stress concentration, they shouldn't go away, because inside the void it should be gaseous hydrogen. But this is something really important to remember, because it helps you to interpret the mechanisms. This is the most modern theory on hydrogen embrittlement. It doesn't necessarily mean that it's correct, but it's the most modern. That supposing you get hydrogen atoms segregating to dislocations, just like carbon atoms segregate to dislocations, then the effect of that segregation, because that reduces the energy per unit length of the dislocation, the effect of that is that basically the dislocation has a weaker interaction with any strain fields, for example, due to precipitates and so on, or solid solution hardening. Therefore, the mobility of the dislocation increases. Now, supposing that your hydrogen is not uniformly distributed, that means in some regions you have a higher hydrogen concentration than other, and in this model they don't explain why you should get that, but let's imagine you have a stress concentration and the hydrogen wants to be in that region. Then if you have a high mobility of dislocations in that local region, you will get a plastic instability, and therefore you will initiate fracture. So that is the mechanism, which is quite fashionable, that you get localized plasticity. In other words, ductile failure. Okay, but like a shear instability, when you fire a bullet at something, as soon as it starts to deform, that region gets hot, and therefore it gets softer, and then you localize the plasticity. So this is known as the HELP mechanism, hydrogen enhanced local plasticity. Okay. This is also a modern mechanism which also requires ductile failure, not cleavage. Okay? And the fractographs that I've seen are pretty convincing that this is not classical cleavage mechanisms operating. For example, here where you see slip striations and microvoids and so on. And the idea here is that hydrogen enhances the vacancy concentration. So vacancy concentrations are very, very low in iron at the temperatures that we are talking about. Hydrogen actually enhances that concentration of vacancies, and those vacancies then condense to give you microscopic voids, so that when you're pulling, these voids basically link up. And because there's a large number density of these voids, therefore you more or less see macroscopically brittle failure. The larger the number density of voids, the less is the ductility, because they don't have to grow much before they link up. And again, you would require a mechanism where hydrogen produces this effect in some localized region where there is a concentration. And I don't have the original paper of this, but the paper describes that if you look at this by atomic force microscopy, you see strings of microscopic voids, which would be consistent with that. So something causes the hydrogen to localize, for example, a stress concentration, and then you create a larger than equilibrium concentration of vacancies, which then condense to give you these microscopic voids, which when you pull, link up by ductile failure. Okay, so the fracture surface will show you ductility rather than cleavage. Okay, so just to summarize, all the evidence points to the culprit being diffusible hydrogen. That means hydrogen which can move about very easily inside the steel. If you try to take it out, you can come out at temperatures less than 100 degrees centigrade. Anything that is trapped in molecular form is not relevant. It doesn't have any influence on the mechanical properties of the ion. It can't move about unless it's in voids which are under extremely high pressure, because they are very small voids. Okay. And same thing applies to strongly trapped hydrogen, because it's not going to move out. So if you have a very strong, and even if it's atomic hydrogen, it can't move, it doesn't do the damage. That we know for a fact. Okay, now let me describe to you a piece of equipment that we have bought in this BP-ICAM project, and we have used in various other places, which is basically a thermal desorption analysis machine. And what it does is you take a sample of steel, you heat it up in a carrier gas of helium, and then at a constant rate, you heat up the sample at a constant rate, and then there's a gas chromatograph which analyzes how much hydrogen is coming out of the steel as a function of temperature and time. So here we have the furnace in which you place the sample and the controlled heating. You have a helium carrier gas, goes into a gas chromatograph, and you basically get outputs like this, which shows you peaks of the rate of hydrogen evolution as a function of temperature or time. So if your hydrogen is weakly trapped, then it will come out mostly at a low temperature. If it's strongly trapped, then it's pushed to higher temperatures. And this is a slight oversimplification, because you can have several kinds of traps and your peaks shape will be affected. You may not see separated peaks, just like in X-ray diffraction and so forth. And I'm going to show you, so this is what the equipment looks like physically. This is your furnace, and this is the gas chromatograph, and there's a computer over there. So it's quite simple, but extremely accurate equipment. You're measuring in the carrier gas concentrations of 0.1 or less of 0.1 or less ppm of hydrogen in the helium gas. Here's an example. This is a particular steel, which is a bearing steel, a common bearing steel, and this is a steel which I'll show you the structure of later. Obviously, this has strong traps for hydrogen, because the hydrogen is being evolved at a higher temperature, and this means a very strong trap. And hydrogen that's located in those traps is not going to influence the properties of the steel, whereas this is highly diffusible hydrogen and will cause damage to your material if it goes into the steel. So what's the difference between these two? Well, this is vanadium carbide particles, vanadium molybdenum carbide particles, which are semi-coherent, and they have strain fields around them. And they're designed so that they form traps for hydrogen. So the problem arose that when you make really strong bolts for bridges and so forth, after a while they just break. That's called static failure. And the point where they break, the point in time where they break, can be quite scattered. So it could be 3 weeks, it could be 3 years. So that's bad. Okay? And what's happening is that hydrogen gets into the steel from the environment, and this is a really strong bolt, and therefore it's embrittled and it fractures. Introducing these particles gives you a large trapping capacity. So this is a large trapping capacity where you're talking about, say, 8 parts per million by weight of hydrogen can be absorbed at those carbides, and it more or less removes the static fracture problem from these bolting steels. So this is now actually, for many, many years, it has been a commercially available product. And we want to do something like this for some of the work that we're doing in this BP-ICAM project. But the theory that goes behind these curves is not well established. And let me tell you why. One of the most common equations that's used to analyze the thermal desorption spectra is called the Kissinger equation. And the Kissinger equation was originally derived for chemical reactions. So supposing I have a test tube with a pink material and it turns blue. Yeah, that's what we call a first order reaction. So it's happening throughout your assembly, and there's no nucleation and growth involved. So there's not one region which starts to turn blue, but the whole solution goes blue. Of course, Kissinger's original equation could be applied to any order of chemical reaction, but it is still a chemical reaction happening fairly homogeneously. So in this equation, this is the heating rate, and this is the peak temperature from your TDA curve. And from that, you get a binding energy. There's nothing in this about the shape or the size of the specimen. If I put a square specimen in TDA, I will get a different result from a cylindrical specimen. And the chemical reaction analogy simply isn't accurate because we get diffusion, okay, from inside to the outside. A more elaborate theory deals with local equilibrium. That means that you have a trap and you have the lattice in which you have diffusible hydrogen, and they will be at equilibrium. So this is the amount, the fraction of hydrogen trapped at traps, and this is the hydrogen inside the lattice, and this is again the binding energy of hydrogen to the trap. And there's a further version of this which allows some kinetics. In other words, hydrogen atoms have to jump over a barrier into the lattice. But all of these deal with a single trap, whereas the real material has multiple traps. So we have been working on this theory, and we have just published a paper on the analysis of TDA curves, and you can see that peak shapes will depend on the distribution of activation energies that we have in the traps, and we hope to use this theory now to actually examine in more detail the spectra that we get from TDA, thermal desorption analysis. This is, of course, a numerical model, because as soon as you get to more complexity, it's difficult to express things analytically. Yeah, it's much easier to do it numerically. And the computer programs for this are available on our website. Okay. I've shown you one method of dealing with hydrogen, and that is to introduce traps. And I want to show you another method in which we introduce barriers to the movement of hydrogen into the steel. And the structure that I'm going to describe is bainite, where we form a plate just like martensite and allow the carbon to partition, and then it may precipitate to form carbides. But you can stop this reaction at this point by adding silicon to the steel, which stops the cementite precipitating, and then you get a structure which looks like this, a very nice composite where you have these layers of austenite separating very fine plates of bainite. Now, how is this relevant to the hydrogen issue? Well, I pointed out to you that diffusion of hydrogen through austenite is incredibly difficult. Yeah? So supposing you have some sort of mechanism of hydrogen getting into the steel, like corrosion, but you have these continuous layers of austenite, then you may not actually be able to absorb that hydrogen. It's like a barrier, a diffusion barrier. And the work that I'm going to show you is not really on this steel where you have a 1/4 micrometer thick plates. But watch this next micrograph. Okay, are you ready to see this next micrograph? This is something that I really like to show many times. This is the world's first bulk nanostructured material. There is nothing to match this. We can make it in thousands and thousands of tons. Indeed, it is made in thousands of tons, where the plates are actually finer than carbon nanotubes. But this is incredibly strong stuff. It's more than 2,000 megapascal strong. So it will have all kinds of problems with hydrogen, we imagine. Okay. So the idea is, idea was to understand the ductility of this material. The ductility varied according to how much austenite we introduced into the material. This is austenite and this is ferrite. And this is without charging. Okay? So imagine that we start off with these 3 levels of austenite in the material. When we pull, the amount of austenite decreases because it undergoes transformation under stress. Okay? So this is how the austenite should decrease as a function of strain. And when we look at the point where these samples break, and we've done this also in situ in a neutron reactor so that we can follow these curves as they happen. Basically, they all fracture when you reach a retained austenite fraction, which is about 0.1. Okay? So what's magical about this 0.1? This is the in situ experiment inside the neutron diffraction kit, where we pull the sample, and again you can see that fracture actually happens when the austenite content decreases to about 0.1. Okay, imagine this is our structure. The blue phase is the austenite and the white phase is the ferrite. In this structure, I can draw a continuous line through the austenite. So imagine that this is now a tree. If I start a fire here, it will spread. Right? So we say that the fraction of austenite here is above a percolation threshold. On the other hand, here I cannot draw a continuous line through the austenite, the red phase. Okay? So here if I start a fire, it's not likely to spread, and that's why we have fire breaks in woodlands. So the idea was that once you lose continuity through the austenite, you're actually stressing the martensite that is formed and also the ferrite, which is also very hard. So then you get fracture. So we wanted to probe this percolation. And what better way to probe it than to introduce hydrogen and see how it behaves? This is just percolation theory to say, which indicated that 0.1 was about the right value of austenite needed. And this is equipment we don't have, but we did the experiment somewhere, but you have it. And it's a different kind of equipment where you look at the permeation of hydrogen through a thin sample of steel. So you introduce hydrogen from one side and you pick it up on the other side. So you're actually measuring effectively the diffusion coefficient of hydrogen through the material. And I'll show you some results from this as well. Okay, so here are some calibration experiments first. So we do not want to saturate the samples before measuring the TDA. Because if you saturate, then you've filled everything with hydrogen, austenite, ferrite, and the barrier effect becomes less significant. So we chose a sample thickness, which is 4 millimeters, compared with 1 millimeter, where we wouldn't saturate the whole sample, and the hydrogen can still move about without reaching solubility limits. If it had been 1 millimeter, we would have had a lot more hydrogen inside the sample during charging. And this experiment is simply to show the reproducibility. Okay, so 2 independent samples with the same heat treatment condition, same retained austenite content, you will get differences, okay, for whatever reason. Okay, then we controlled the amount of austenite, and if the percolation threshold for austenite is 0.1, that means if the retained austenite content is less than that, then the hydrogen has a free path through the ferrite, which is a fast diffuser. So this is a sample which has a fraction of austenite less than percolation, and here is higher than percolation. And you can see there is a significant difference. This continues to absorb hydrogen when we charge it. This levels off. Okay. Similarly, here is a plot of the total amount of hydrogen released between 0 and 300 degrees centigrade as a function of the fraction of austenite. And if you use your imagination, you can see that there is a significant change when we go below the percolation threshold. So this is a large difference here. So it seems to be correct that this structure will lose percolation when we go below approximately 0.1 of austenite. Then we used the equipment that you have here for measuring permeability through the sample. And you know, when I showed you the slide of diffusion through ferrite and diffusion through austenite, the difference was huge. And if we assumed the diffusion coefficients in that slide, then as soon as we lose percolation, you know, you would get a massive increase in the permeation of hydrogen. But if you have things like traps, then the difference will not be as large, because the activation energy for diffusion, the apparent activation energy for diffusion, will be much higher than just for diffusion in ferrite. That was the gray shaded region that I showed you in the slide. So we did some calculations accounting for the trapping for these three scenarios. Here you have a continuous layer of austenite separating the ferrite, and therefore you should have low permeability. If you had a structure like this, the austenite would have no influence at all. And if you take this sample and you reduce the quantity of austenite below the percolation threshold, and there's a reason for choosing this fraction as 0.3, you would get approximately a doubling of the permeability of austenite as soon as you lost percolation. And that is what you see. So ignore these points and this picture for the moment, but you can see that there are actually two different kinds of diffusion coefficients that you get from this equipment. One is called the breakthrough, where, you know, basically when does hydrogen actually start entering? Correct me if I'm wrong. You know, if there's a film or something, it breaks through. And the other one is when it's entered the steel and it's actually moving through and coming out onto the other side. But both of them show exactly the same trends. If you focus on these data, that you get an increase in permeability when you go below the percolation threshold. Now, here I was talking about layers of austenite which act as barriers. Okay? But supposing you have a high volume fraction of austenite, but it's distributed as blobs. This is another steel where we have 26% austenite, but clearly it does not form a barrier. Then, of course, we have a high permeability through that structure. So the morphology of austenite is as important as having a certain fraction of austenite. The next complication when it comes to complex microstructures is that if you pull and you've got a large concentration of hydrogen in the austenite because you've saturated the sample, okay, solubility of hydrogen in austenite is greater than in ferrite, and the austenite transforms into martensite. You know, you've got a very large concentration of hydrogen in the martensite, and it's going to zip through the structure. Right? So suddenly the diffusion coefficient will be much larger because you've changed the crystal structure. And indeed, that's what you find. This is the specimen which has not been strained. Okay? And these are specimens which have been strained so that the austenite in this particular steel has decomposed into martensite. And you can see that, you know, suddenly the hydrogen becomes diffusible. The hydrogen that was trapped in austenite will become diffusible. So that's a very interesting fact that yes, you want the hydrogen to end up in the austenite because it's a strong trap. But then if you do something to trip the austenite, then you're basically providing an internal source of hydrogen to the ferrite. Not a good thing. So far I've talked about ferritic steels. And until recently I would not have believed that you get hydrogen embrittlement in austenite because austenite doesn't have a ductile brittle transition. But there's a class of steels called TWIP steels, TWIP, twinning induced plasticity, which are fully austenitic. Okay? And they had a bad start, even though they have outstanding properties. They start off at a strength of 400 megapascals, go to a strain which is more than 120%, and work hard into 1,000 megapascals. So beautiful ductility. Yeah? After a while, they started to undergo what's called static fracture. This is fully austenitic, right? And you can see these cups which were drawn, they started to break up. And so this is 22 manganese, 0.6 carbon, and this also has aluminium addition to it. And the problem was dramatically reduced. So why is that? Okay, so the first thing is we took two samples, one with aluminium and one without aluminium. And for reasons which are not clear, the one which is less susceptible to hydrogen actually absorbed more hydrogen. So we cannot say that, yes, aluminium reduces the absorption of hydrogen by the steel, and therefore that's the answer. Okay? So I don't know why this happens, but it happens. Of course, these things deform both by mechanical twinning and dislocation flow. And aluminium increases the stacking fault energy of the material. And there's no strict correlation between stacking fault energy and the tendency to twin. But the fact is that for the same deformation, you get less twinning in this material. And the twinning is actually important in the sense that it leads to a work hardening mechanism, and therefore you don't get plastic instability, and therefore you get a very large elongation. Okay, so we get fewer twins in the aluminium containing alloy. And this is austenite. Okay, everyone would say is nice ductile, no ductile brittle transition, and you can see that in both cases there are brittle-like failure. This is quasi-cleavage type failure, and some of it is transgranular, some of it is intergranular, and so forth. Now, one consequence of hydrogen not being able to diffuse through austenite is there's no way you can charge the whole sample with hydrogen. Only the surface region, about 100 micrometers after 2 weeks of charging, will absorb the hydrogen. Okay, so when you do a mechanical test, it's only that region which is affected. Right? So that's something important to bear in mind. Austenite is a barrier to diffusion. Therefore, you cannot do experiments with thick samples. Okay, there is another technique for picking up hydrogen, and that is by depositing particles of silver from a solution onto the material. Someone doing it here? Okay. So it's very nice because you can actually see where the hydrogen is located. And these are the two alloys. First of all, focus on this. These are silver particles decorating the twin interfaces. In other words, we've got hydrogen segregating to the twins. If we remove the hydrogen, then you don't pick up any silver particles. Just a control experiment to show that if there's no hydrogen, we don't deposit the silver particles. And this is the aluminium containing alloy. Again, you can see hydrogen through the silver particles at those twin interfaces. Now, in the case of the low aluminium alloy, we also pick up actually phase transformation. This is epsilon martensite, hexagonal close-packed martensite forming. So with sufficient deformation, you actually get epsilon martensite forming. It doesn't in the case where we have a large stacking fault energy. So what we did was we examined these by doing focused ion beam, machining out and putting it into the TM to see what those facets actually are. And it turns out, in the case of the epsilon martensite, that the facets tend to be parallel to the habit plane of the hexagonal martensite. In other words, we've got the hydrogen going to those interfaces. And in the case of the high aluminium alloy, parallel to the twin interfaces. The twinning is less sensitive to fracture than the epsilon martensite. So the effect of aluminium in this case is simply to alter the stacking fault energy to eliminate the epsilon martensite and also to reduce the amount of mechanical twinning. Okay, so just to summarize the methods that I've talked about for controlling the consequences of hydrogen. So assume that hydrogen is going to get in. What can you do about it? Well, first of all, if we can introduce traps into the material so that they render any hydrogen that goes in innocuous, we can retard the infusion of hydrogen into the steel by putting a diffusion barrier in the form of austenite layers. And in the case of austenitic steels, we need to control the stacking fault energy and also the phase transformations. Seems very easy, right? But remember that you have to control all the other properties at the same time. So if you alter something, say you control the stacking fault energy and eliminate the twins, you no longer have a trip steel. Right? And if you introduce traps which make the material extremely hard, you might not have toughness and so on. So it's not at all an easy task, but it's one way of controlling the effects of hydrogen as opposed to just understanding what hydrogen does. I have a number of questions to finish with, okay? And the first question is really, really difficult. And, you know, Robert, you're familiar with this. Someone from BP asked, okay, supposing you have these traps and they can hold 8 parts per million of hydrogen, what service life does that give me? And, you know, I just cannot find an answer, right? So, how much hydrogen will get into the pipe over a period of 40 years? We need that information. Okay? So we need somebody to give us a sample which has been in service for many, many decades, and then we should measure the amount of hydrogen. I talked to, Bob is aware of this, I talked to Alison Davenport who passed me on to somebody else who passed me on to somebody else. Tim Burstein had no answer, and so on, okay? So I'm not a corrosion expert, and we need an answer to this question.
Nobody else is.
Manchester has a lot of expertise on the so-called large facilities, you know, like Diamond and so forth. And the issue that I raised earlier about reversibility, you know, that if I take a tensile specimen, I charge it with the hydrogen, but let the hydrogen go away, then the properties will be the same as an uncharged specimen. But supposing you do the same experiment where you have a notch and you stress the sample, then you should have created some voids if void formation is important. Wouldn't it be wonderful if one of your facilities could actually verify that? Then it should not be reversible, actually. So there's ordinary testing to be done and also examination using the large facility. And supposing that the mechanism is vacancy enhancement by hydrogen, can we not do something to kill those vacancies by putting other solutes which want to be with vacancies and so on? So this is all speculation at the moment, and I think it's worth thinking about because we don't want to just understand how hydrogen works. If we can actually cure it, that's an understanding of the problem, right? And I think that is my last slide. Yeah. So I'll be happy to.